Imagine a train traveling at 603 kilometers per hour with no wheels touching the ground, floating on invisible magnetic force through tunnels carved through solid mountain. Now imagine that after spending $72 billion and 60 years of development, one governor with one signature stopped the entire project for 4 years. This is Japan's Chuo Shinkansen Maglev, the fastest ground vehicle ever built, and the story of how it nearly never happened is more remarkable than the engineering itself. If you're fascinated by mega projects that push the absolute limits of what humans can build, hit that subscribe button because we're diving into the engineering marvels that redefine what's possible. 1964. Japan launches the bullet train and changes the world forever. Then they ask themselves, what's next? The problem is immediate. The Tokaido Shinkansen is running 12 trains per hour. There's no more capacity. Japan needs a bypass, but the coastal route curves around mountains. The solution? Cut straight through them with magnetic levitation. Research begins in 1962. It will take 63 years to turn those equations into an actual railway. In 1977, the first test track appears in Miyazaki, just 7 kilometers long. The first levitation happens, the first proof that superconducting magnets can actually hold a train in midair. It works, but proving it on flat ground in Miyazaki is one thing. The real challenge is the Japanese Alps. 1990. Geological surveys begin. 19 years of surveys before a single tunnel gets approved. The geology under the Southern Alps is 300 million years old. Unlike anything engineers have ever tunneled through before, 1,400 meters of mountain overhead, fault zones, underground rivers, rock pressure that can crush steel. This isn't just difficult, it's borderline impossible. May 27th, 2011. After 49 years of research, Japan approves the Chuo Shinkansen. Construction can finally begin. But first, they need to prove everything one more time. The Yamanashi test track comes first. 18.4 kilometers of real Maglev railway built to validate every system. 11 kilometers of test tunnel get drilled using the new Austrian tunneling method. Drill, blast, muck out the debris, spray shotcrete, install rock bolts. Repeat. 6 hours per blast cycle, every single day. A pilot tunnel drills first, sampling the rock before the main machine commits. The guideway must be accurate to millimeters over kilometers. Laser checks every single section. Here's where the engineering gets wild. Figure 8 coils are embedded in both walls. Levitation, guidance, and propulsion all in one coil design. The motor isn't in the train, it's in the track. 18 kilometers of electric motor embedded in concrete. Every coil powered, every sensor connected before a single train runs. The first test train arrives in 1995. No visible wheels, no pantograph collecting power from overhead wires. A capsule designed to float. First. Levitation happens in 1997. The tires retract. The train rises 10 centimeters, floating on invisible magnetic force. December 1997, 531 kilometers per hour. A new world record on their very first full-speed test. 200,000 people ride the test train before commercial service even starts. Japan tests everything. October 2014, ground breaks on the real line. 286 kilometers from Shinagawa to Nagoya, 246 kilometers of that inside tunnels, 86% underground. This is the biggest railway project in history. The new Shinagawa station goes under the existing bullet train station. Construction happens without stopping the trains above. Diaphragm walls first, continuous concrete retaining walls built before excavation begins. 40 meters deep beneath a live railway station in central Tokyo without causing a single delay above. The tunnel boring machine assembles underground, too large to lower whole, piece by piece in the launch shaft. 14 meters wide, 150 meters long, 4,000 tons. 80 tungsten carbide disc cutters on the face. The machine advances 15 meters per day through urban ground. Above it, homes, shops, people who feel nothing. One concrete ring installed every 90 minutes. 6 segments per ring, 600 rings per kilometer. Urban soil becomes alpine rock. The TBM slows. Disc cutters wear every 50 meters and must be replaced. Replacing cutters requires entering the pressurized chamber at the tunnel face, one of the most dangerous jobs in construction. A pilot tunnel drills 1,000 meters ahead, reading the geology before the main machine arrives. Then the geology fails. Schist rock, 300 million years old. Fractured, unpredictable, unlike any model predicted. Emergency redesign. The new Austrian tunneling method replaces the TBM in the worst sections. 5-year delay announced. 1,400 meters of mountain overhead, creating rock pressure that crushes the tunnel like a vice. Steel arch ribs get installed, where rock pressure peaks. Then shotcrete, then rock bolts, then more shotcrete. Underground rivers encountered at depth, grouted shut, drained away. The mountain fights back constantly. 10,000 liters per minute pumped from the Southern Alps tunnel, every minute of construction. 3 different tunnel boring methods used in one project. The geology forces every change. Excavated alpine rock gets crushed on site, reused as concrete aggregate in the tunnel lining itself. 400-meter vertical shafts sink through the mountain for ventilation and emergency access. 60 separate construction contracts, all running simultaneously. Underground stations carved from solid rock. The Kofu station, bigger than most surface stations. No columns support the station roof. Rock anchors drilled 20 meters into the mountain do the work. A complete railway station built inside a rock cavity, 40 meters underground with no natural light. Tunnel complete. Now the hardest part. The guideway must be installed to millimeter accuracy over kilometers. Every section laser surveyed. Tolerance 1 millimeter over 50 meters. 0 exceptions. 580,000 individual coils installed in the guideway walls, everyone positioned by hand. The engine is in the ground, not the train. 246 kilometers of electric motor embedded in concrete. The nose is 15 meters long, shaped in a wind tunnel for 3 years, designed to enter a tunnel at 500 kilometers per hour without creating a pressure wave that damages eardrums. Niobium titanium wire, thinner than a hair wound 50,000 times per coil in a vacuum environment. The cryostat keeps the magnet 4 degrees above absolute zero. Liquid helium loaded at negative 269 degrees Celsius, colder than the surface of Pluto. The magnet becomes superconducting, 32 superconducting magnets per train. Below 160 kilometers per hour, rubber tires. Above that, the tires retract automatically. The train floats, entering a tunnel at 500 kilometers per hour, compresses the air violently. The cabin pressure system prevents ear damage. Inside, it looks like any other train. The engineering that makes it extraordinary is completely hidden. First test at walking pace. Every sensor verified before speed is applied. 160 kilometers per hour, tires retract, the train rises. 200, 300, 400, 500. The data confirms what the physics promised. A magnet quenches at 400 kilometers per hour. The safety system activates. The train stops safely. Engineers redesign the magnet mounting. Problem solved. April 21st, 2015. 603 kilometers per hour, a world record. The fastest land vehicle in human history. Inside at 603 kilometers per hour, almost no vibration. Passengers could read a newspaper. That is the engineering. Then in 2013, one governor of Shizuoka Prefecture says no. 620,000 people's water supply is the reason. Engineers design a system to return every liter of groundwater captured during tunneling back to the river. Not good. Enough. Construction stops. 2027 becomes 2034, then 2035. Every year of delay, billions more in cost. $9 billion becomes $72 billion. April 2024, the governor resigns. The market knows what it means. JR Central's stock rises immediately. The new governor approves the survey within weeks. After 4 years, construction resumes. October 2024, first boring survey equipment enters Shizuoka. 4 years of delay finally over. Japan has a severe construction labor shortage. Some tunnel sections run at 60% crew capacity. 30,000 construction workers across 60 sites. Most will never ride the train they built. At 500 kilometers per hour, noise barriers reduce trackside levels below 70 decibels. Quieter than a busy road. China unveils a 600 km per hour Maglev in 2021. Japan invented this technology. Now it risks losing the race to open first. 2025, 60% of tunneling complete. Target commercial operation 2034. Everything built so far is waiting for the train that will make Tokyo and Nagoya 40 minutes apart instead of 90. Now, here's a question for you. If you were leading this project and faced the 4-year Shizuoka delay, which approach would you prioritize? Option A, reroute the tunnel to completely avoid Shizuoka Prefecture, adding distance and cost but eliminating political risk. Option B, invest heavily in even more advanced groundwater protection systems to convince the governor, accepting the delay but staying on the planned route. Option C, Build everything except the Shizuoka section and open a partial line, generating revenue while negotiating the final segment. Drop your answer in the comments because I'm genuinely curious which strategy you think would have gotten this engineering marvel operational faster.